Hello everyone, welcome back to my channel Higher Mathematics. Today we have a very tricky exponential equation 1 to the x equal to 2. And a lot of students might be saying, hey mister, there is not possible, 1 to the x cannot be equal to 2. And here's my answer. Everything is possible in math. So right now let's look at my solution, let's look at my thought about this question. So first of all, let's apply natural log on both sides. Let's do this right now. So when we apply natural log on the left side, we have natural log of 1 to the x equal to natural log 2. Right now, according to a log property, this x will come down right here, so we can easily write it in the front of it because this is like the main log property. As a result, what do we have? X times natural log 1 equal to natural log 2. And right now, let's divide both sides by natural log 1 because we need to find our x. Let's do this right now. So when we divide both sides by this natural log 1, as a result, what do we have? X equal to natural log 2 over natural log 1. And here is the tricky moment. Natural log 1 equal to 0. But in terms of real numbers, we can't divide by 0 because we have natural log 2 divided by 0. So right now we can easily see that right here there are no real roots. But as I told before, everything is possible in math. So right now I'm going to show you my notes, my thoughts about this question. So first of all, let's write Euler's identity. This identity looks like that. So let's separate our solution. So first of all, Euler's identity. We have e to the power I times theta equal to cosine theta plus I sine theta. This is our Euler's identity. This looks like a special case. And right now let's check this identity really quick. Of course, if you don't trust me, we can easily check it. So for example, theta, for example right here, so 4 theta equal to 0. What we'll have as a result? We will have e to the power I times 0 equal to cosine 0 plus I sine 0. Right here, what do we have? E to the power 0 equal to 1 we have on the left side, and on the right side we have cosine 0 equal to 1 and plus I sine 0 equal to 0. So as you can see, this identity works perfectly. We don't need this special case, but I just want to show you that this identity is correct. So right now we know that identity is correct. This is Euler's identity. Of course, this is correct, yeah. And right now let's write our substitution. My substitution looks like that. So let's split this part right here. So this is about Euler's identity. And right now let's write our substitution. So theta equal to 2k pi. And of course we are talking about k is z, yeah, k is integer, and of course we are talking about k equal to 1 times 2 times 3 and dot dot dot, a lot of these values. So this is our substitution to our question. So instead of this theta right here, let's plug in my substitution. As a result, what do we have right here? We have e to the power I times 2k pi equal to cosine 2k pi. We are talking about substitution, so cosine 2k pi plus I times sine 2k pi. Okay, I just write my substitution. Okay, I hope you understand it. Instead of this theta, I write this substitution, theta equal to 2k pi. And right now here is a tricky moment, okay, because I'm going to talk about special cases. So let's see what will happen. So first of all, let's see what will happen when k is equal to 1. So for k is equal to 1, let's see what will happen when k is equal to 1. As a result, what do we have? E to the power I times 2 pi equal to cosine 2 pi, because k is equal to 1, so we have cosine 2 pi plus I sine 2 pi. Okay, and let's see what will happen. Cosine 2 pi, sine 2 pi, we can easily find it. So first of all, what do we have? Cosine 2 pi equal to 1, okay, and sine 2 pi equal to 0. So as a result, we are talking about 1 plus 0, which is equal to 1. So when k is 1, this expression on the left side is equal to 1. Really great. But right now, let's see what will happen. Let's find this pattern. But first of all, let's find our for k equal to 2. Let's see what will happen when k is equal to 2. We will have as a result e to the power I times 4 pi. Yeah, as a result, we have I times 4 pi. Yeah, equal to cosine 4 pi, okay, cosine 4 pi plus I times sine 4 pi, okay. And right now let's look closely. This is just a period, so this is also equal to 1, and this is also equal to 0. This is like a period of sine, okay? And right now 1 plus 0 equal to 1. And as you can see, when k is equal to 2, this expression on the left side is still equal to 1. Okay, let's see what will happen when k is equal to 3. So one more k equal to 3. So 4k is equal to 3. As a result, what do we have? E to the power 6 I times 6 pi, e to the power I times 6 pi on the left side we have, equal to cosine 6 pi, okay, cosine 6 pi, and plus I times sine 6 pi. And right now let's look closely. What do we have? Cosine 6 pi equal to 1, and sine 6 pi equal to, right here we have 0. So 1 plus 0 equal to 1. And here is the main note for me. When k is equal to 1, 2, 3, so according to our substitution, all the time this expression on the left side is equal to 1. And we don't need to check our k is equal to 4, because we will have like 8 pi, 10 pi, 12 pi, like 14 pi. So as you can see, it's just like a period of this sine and cosine. So this expression on the left side, this one, equal to 1 when k is integer. So here is the main note from me. So let's write it. So this expression on the left side, e to the power I times 2k pi. So let's split this part, because this is like a proof. We have right here e to the power I times 2k pi equal to 1. Okay, after all of this proof, this expression is equal to 1 when k is z. Okay, and right now here is the main thing. In the beginning we had an equation 1 to the x is equal to 2, and this 1 is equal to e to the power I times 2k pi. Right now we know that we don't have real solutions, and right here we have a complex imaginary part. So right now let's try to find our complex solution. We know everything about real number solution, we don't have it, and right now let's solve it in terms of complex numbers. For this expression is equal to 1 when k is integer. So right now let's plug in, instead of this 1, let's plug in this e to the power I times 2k pi. Let's see what will happen. So instead of this 1 right here, we're gonna plug in e to the power I 2k pi. Okay, so as a result we have e to the power I times 2k pi. We're gonna raise this to the power x, and this is equal to 2. Right now let's solve it. Let's see what will happen when we solve this equation. First of all, we're gonna multiply our powers, because we're talking about a rule, a to the power x raised to the power y. We just need to multiply x times y. So in our case we're gonna multiply our powers. So we have e to the power I 2k pi, I times 2k pi, and of course times x equal to 2. All right, right now what we're going to do, first of all, let's apply natural log on both sides. Okay, let's do this right now. We're gonna have like natural log of e to the power I 2k pi x, this our power, equal to natural log 2. Okay, and right now this long and complicated power we can easily write in front of this natural log, okay, because this is like a basic natural log property from school. We have natural log, okay, I write it right here. I hope you understand it. So we have natural log of, right here we have p, right here we have n. We can write it as n times natural log, right here we have p. Okay, so here's our property. That's why I write this I 2k pi x in front of this natural log e. So we have I times 2k pi x times natural log e equal to natural log 2. All right, this natural log e is equal to 1. Yeah, so we can easily cancel this natural log e, and right now we have I 2k pi x equal to natural log 2. Let's write it right here on this part. So we have I 2k pi x equal to natural log 2, I times 2k pi x equal to natural log 2. Right now let's divide both sides by this I 2k pi, because we need to have only x on our left side. So let's divide this one by I 2k pi and this one by I 2k pi. We're gonna cancel this from the left side, and as a result what do we have right here? That our x is equal to natural log 2 over I times 2k pi. And right now let's multiply the numerator and denominator by I. Okay, let's do this. So let's multiply right here by I and right here by I. When we multiply it in our denominator, we will have I square, and in terms of complex numbers everyone knows that I square equal to -1. So the main sign will be negative, and we have I times natural log 2, I times natural log 2 in our numerator, and in our denominator we have 2k pi. This is our final answer, but don't forget about one really important moment. So first of all, let's write our final answer right here. Okay, let's split this part and let's write our final answer. So our answer to this question. So first of all, x is equal to minus I times natural log 2 over 2k pi. But don't forget about really important rules. So first of all, k is not equal to 0, okay, because we have in our denominator. Let's write it. Don't forget about it. K is not equal to 0. And secondly, k is z. So we are talking about integers, okay? So k is integer value. So k is integer. And here is the main note from me. This is not a general solution in terms of like we can easily say what will happen when k is equal to 1.5, like k is not integer, we don't know about it. We know that when k is integer, when k is not equal to 0, we are talking about this x. It takes place because we solve it according to a complex numbers. Everything is great, I guess, but we don't know what will happen when k is equal to, for example, 3.5 minus 2 minus 9. We don't know what will happen about then when k is a negative, because we solve it according to an identity where k is integer. But what will happen when k is, for example, negative, when k is like decimal, when k is like a fraction? We don't know about it. So if you have your thoughts about it, you can also write your notes down into the comment section. It will be really interesting to exchange information. And here's my solution. I hope you understand it. I hope you learned this Euler's identity. I hope you understand these special cases when k equal to 1, 2, 3, every time we have 1. So as you can see, we can easily take this expression on the left side, in our case e to the power I times 2k pi, and we can easily plug in this instead of this 1. In the beginning, we know that we don't have real number solution, so as you can see, this complex number solution also takes place because we solve it according to a correct identity, yeah? And what will happen when k is 1.5, 3.5, minus 100, minus 1 million? We don't know about it. We know when k is integer. So here's my notes, here's my solution to this question. So also write your notes, also write your thoughts down into the comment section. What do you think about it? It will be also really interesting to read about it. Thank you everyone for your time, love math, and have a great day.